Welcome to Khetz and in this video I'll be talking about the converse of Theorem 2, which I previously discussed. So we're going to talk about Theorem 2's converse, right? So that is Theorem 2 and we're dealing with the converse of that. So let's get right into it. The converse of Theorem 2 says if the corresponding sides of two triangles are in proportion, excuse me, then the triangles are similar. Okay, so that is what the converse is saying. It's basically saying if the corresponding sides of two triangles are in proportion, then the triangles are similar. So our task now is to actually see if this is true. And to find out if that is true, actually gonna do a proof for this. So in the proof, we know that we're actually given that corresponding sides are in proportion, as the first part of the statement says. So I have two triangles over here as required by the statement. So it says if the corresponding sides of two triangles, so two triangles, and are in proportion. So let's finish that sentence or that part. Are in proportion. So we have two triangles. We've already dealt with that. Let's call this A, B, and C. Here we're gonna have P, let's say Q and R. We have two triangles. And these two triangles, we're given that they're actually in proportion, which means AB divided by PQ is equals to AC divided by PR, which is also equals to BC divided by QR. So that's the first part of the theorem. It says if two triangles are in proportion, so we have two triangles and we have the proportion over here given to us, then the triangles are similar. Now the last part is the part which we are unsure of. Then the triangles are similar, and therefore we want to prove that the last part is actually true. So in our proof, we're actually required to prove that triangle ABC is similar to triangle PQR. And to effectively do that, we're going to make a construction here. So we're going to make a construction and we're going to call this S. This part here, we're going to call it S. And we've made that construction such that, so construction, made the construction such that we have our angle A equals to angle S and angle B equals to angle Q and this is in the construction, and that construction is triangle SQR. So this Q refers to the Q associated with the triangle SQR, and finally our construction gives us C equals to R, and this R as well is also in SQR. Now we have all these angles equal, right? And we know that for similarity, if we have all angles equal, then the sides are proportional, and finally the triangles are similar. We've actually covered that in Theorem 2, because Theorem 2 actually says that if two triangles are equiangular, then their corresponding sides are in proportion and the triangles are similar. So from theorem 1, we can say that triangle ABC is similar to triangle SQR. The reason for that is angle, angle, angle. Because we made a construction such that this angle would be equals to that angle. This angle would be equal to that angle. So this is from the construction that we actually made ourselves. So we forced this to be true. We forced the angles to be equal. And now that the angles are equal, we have similarity between the two. So between the construction and ABC. But we haven't answered our question, or we haven't proved what we want to prove. We ultimately want to prove that ABC is similar to PQR. Now we've only proved that ABC is similar to SQR, which is our construction. Now from here, this similarity of the construction and ABC is actually going to help us further. And this is how it's actually going to help us. Now that we've identified that ABC is similar to the construction SQR, we can therefore say that AB, so AB divided by SQ is equals to BC divided by QR, which is equals to AC divided by SR. And this is from the similarity, which is over here. This is the conclusion that we can make from the similarity. Now, if you look at the proportion which is given to us in the question, which is over there, and the proportion which we've currently established over here, you'll notice that there's actually a common term, and that common term is BC over QR. We also have BC over QR over here. And therefore, we can equate these two proportions because we have the same term BC divided by QR in both of them, which means our given proportion in the question, so you can even come up here so that we have all of that. So our given proportion, which is in the question, AB divided by, so I'm just copying this, AB divided by PQ is equal to AC divided by PR, can be equated to all of this, which is down here at the bottom. It can be equated to all of this, right? And we can therefore say all of that is equals to the newly found proportion AB divided by SQ equals to AC divided by SR. And this is only because these two have a common proportion BC divided by QR. So all of this is equal because all of them are equal to BC divided by QR. We have BC divided by QR at the top in our given proportion, and we have BC divided by QR at the bottom in our established proportion, which means all of that is the same or is equal to each other. And from that, if we just look at the common terms, we have AB at the top, we have AB at the top over there, which means the bottom has to be the same, which means PQ is equals to SQ. So you can make that conclusion, therefore PQ is equals to SQ. And we have AC there, we have AC there, we have PR and we have SR, which also means that PR is equals to SR. Then finally, we have this common side. If you just come back to the diagram, if you look at QR, it's actually a common side. It's common between PQR and SQR. You have it over there. It's common. It's a common line. QR is a common line. And we can finally say that QR is equals to QR. Now, this is leading us to this conclusion that we can make. We can make this conclusion that triangle PQR is congruent to triangle SQR. And the reason for that is side, side, side. So PQ, if you come up here, PQ is equals to SQ, and PR, right, is equals to SR, and QR is equals to QR because it's common, right? So you can also give a reason here if you like. Common side right? And we can finally say that the two triangles PQR and SQR are actually congruent. So they're exactly the same. So now that we've established that, we also previously established that ABC is here. We previously established that ABC is similar to SQR. And now we said that PQR is actually the same, exactly the same as SQR. So previously we established that SQR and ABC are similar. And now that we've established that SQR and PQR are the same, this means that ABC and PQR are also similar. And that means we have finally proven that ABC and PQR are similar. If ABC is similar to SQR, then it's also similar to PQR because SQR and PQR are the same. They are congruent from this conclusion that we previously made. So that is basically all that I had in this question. I just wanted to explain the second theorem, the converse of the second theorem, that is, and also prove that it is actually true. So if anything is not clear in this video, please leave a comment. And if you like the video, just go ahead and give it a thumbs up. And I will see you guys in the next video. If you haven't subscribed, please subscribe.